All right, guys. Today begins your first day of virtual learning. I hope nobody has PTSD from COVID times, but we got to do what we got to do in times like these. So here we go. All right. So yesterday you should have taken your topic 6 test, and your sub should have given you the 9.1 notes. Today, we're going to kind of go through the first part of it, and then I'll give you a little overview of what we're going to be doing. So I had to change this kind of last minute because of the hurricane. So in the next video lessons, the dates are going to kind of be off. So today, what you're going to do is watch the lesson in Schoology, and then on the 5th, there will be another Schoology lesson, and then for homework, you will prep the single replacement lab that you'll be doing on the 6th in class. And then for homework, you'll work on that lab report, and that's actually going to be due on the 13th. And then on the 7th, you'll have all day in class to work on that lab report. And then on the 8th, there will be another Schoology lesson for you to watch. And then I'll be back on the 11th. So, and on the 11th, we'll go over kind of everything that you learned from me virtually while I was gone, and kind of wrap up any questions you may have. The topic 9 and 19 can be kind of confusing because oxidation and reduction always go together, which is good because if one thing is getting oxidized, the other thing is getting reduced. But the process gets a little complicated later in the lessons. You'll kind of see what I'm talking about. But for this one, you're going to have to study a little bit more and probably review every day. This is getting into like that super advanced chemistry concepts, where it's not something that you will have learned in honors chemistry. So it's all going to be pretty new to you. So you'll have to do a little extra studying. So when it comes to the understandings for this topic, oxidation should sound like something to do with oxygen. And so that is true. It's kind of an old definition though, but you can look at oxidation in terms of oxygen gain, but we've changed the definition of oxidation and reduction to not include oxygen because every process doesn't have to have oxygen involved. So we broadened that definition to now include not only oxygen gain or oxygen loss, but the transfer of electrons and what's happening with those electrons, which then in turn changes what's called the oxidation number. This in gray right here, you need to circle, underline, star, highlight this because this is a concept that we will keep coming back to. But an oxidizing agent is reduced, and I'll explain what that means later, and a reducing agent is oxidized. So this is that part in this topic where I say it gets a little tricky because it doesn't seem very straightforward, but once you see it kind of worked through as a concept, you'll be like, oh, okay, I get that. That makes sense. But for now, just circle this statement in gray here. We're going to talk about oxidation numbers and how to find oxidation numbers today. And then later we'll talk about the activity series, which is how we can rank how easily metals undergo oxidation. And then we'll talk about the Winkler method when I get back and how we can use this in environmental chemistry. All right, so as I was saying in kind of the intro, old school terms when we talk about oxidation versus reduction is oxidation originally was just something that gains oxygen. And if something is gaining oxygen, that oxygen has to come from somewhere. So the thing that's losing oxygen is undergoing reduction. So just kind of like when you buy a pair of socks, they always come in twos. Oxidation always is accompanied by reduction. So if the thing is being oxidized, then the other thing must be undergoing reduction. But kind of like with our understanding of acids and bases, this definition did not could not be applied to every chemical reaction because not every chemical reaction includes oxygen. So we've since changed the definition to not involve oxygen at all. And oxidation is actually when something loses an electron. And when something loses an electron, that means it's losing a negative, so it becomes positive. And when we say reduction now, we're looking at something that gains electrons, which means it becomes negative. So let's pause just now and talk about that. So if something is getting reduced, what happens? It becomes less. So reduction means that it's becoming negative because it's becoming less because it's gaining negative electrons. So something that my chemistry teacher taught me that I think has, helped remember this process is something called oil rig, which is why there's an oil rig over here. But oil rig stands for oxidation is loss. What is it losing? Electrons. Rig is reduction is gaining electrons. So if you can remember oil rig, oxidation is losing electrons and reduction is gaining electrons, then you should be good to go. So this gaining and losing of electrons can result in a change in electricity, which it means we'll be talking about batteries in the next topic 9.2, and also something called electrolysis, where we can use this gaining and losing of electrons to power chemical reactions, which is pretty cool. So let's kind of look at this gaining and losing as an example, because I think it's easier to see it all written out. So in this blank page in your notes, let's do a little example here. So we'll start with a simple chemical reaction that you guys have actually done in an experiment. So here's your chemical reaction. And what we see on the reactant side is we have two reactants. We have magnesium and we have oxygen. So if you look at magnesium on the left-hand side, it does not have an oxygen attached to it. But if you look on the right-hand side, you see it has now gained an oxygen. So if we go back to our old school definitions of oxidation and reduction, oxidation means we've added oxygen. So here you see magnesium without, and now it has gained an oxygen. So by the old school definition, magnesium undergoes oxidation. And that's once again because it has gained an oxygen on the product side. You can see it there. Now here's oxygen, just plain old oxygen. There's two of them. And if you see on the right-hand side, it's actually lost. I know it looks like it's lost in oxygen, but in fact, it's just lost it because now it's magnesium has bonded with it. But here, oxygen was two oxygens. Now it's only one. So this means that it undergoes reduction because it has lost oxygen. Now that's in terms of its old school definitions, but let's look at an example where there's not an oxygen involved at all. So we'll keep with the theme of magnesium. All right, so this one isn't very clear as to what's getting oxidized and what's getting reduced because there's no oxygen involved. So for that, we actually have to use our new school terminology. So this time we got to figure out what's losing electrons and what is gaining electrons. So here, magnesium on this side, it is a neutral substance. And so because it's neutral, its charge is 0. But if we look on this side, magnesium is now in a compound. And magnesium, in this case, when it forms a compound, we got to look at the charge. So on your periodic table, magnesium is in group 2. So in a compound, magnesium's charge is +2. So we see on this side, it goes from neutral magnesium with no charge to now being in a compound, magnesium has a charge of +2. So it's gaining, its charge is going up. Here we have nitrogen is also neutral. And so its charge is 0. But here nitrogen is in a compound. So here its charge is -3 because it's in group 15 and has a charge of -3. So what we do is we compare what happened to our changes in charges. And what we see is nitrogen, its charge becomes more negative. So if it's becoming more negative, that means it's undergoing reduction. And magnesium, if its charge is going up, that means it's undergoing oxidation. So if you don't get this right away, don't worry, we're going to do lots and lots of practice, and eventually it's going to like little light bulb on your head. So you're going to hear me say charges and oxidation numbers. They are kind of the same thing, but not the same thing at all. So I can already hear and see those evil looks like at me going like, what are you talking about? So oxidation numbers only are in reference to redox reactions, oxidation reduction reactions. So the plus and minus mean the same thing as when we were talking about charges last year. So a positive means that it's lost an electron, kind of like a cation is positive because it's lost an electron. Negative means it's gained an electron, just like an anion is negative because it's gained an electron. So here is an example of oxidation number versus charge. The part on the left here, you see that the charge is written in the front of the number. So it says +2. If the charge is in the front and the number is in the back, that means that you are writing an oxidation number. If you write it the other way with the number in the front and the charge in the back, then that is representative of a charge. Now, calcium has the same oxidation number and charge. Sometimes that's not always the case, and we'll talk about those cases in just a minute. But the oxidation state of calcium, because chlorine is -1, the oxidation state of calcium has to be 2+, which is also the charge of the calcium ion. So I know this is like, well, why IB, why? I don't, I don't know. I think they're trying to make your lives more difficult. But please try to make a concerted effort. And I'm really bad at this because I'm slightly dyslexic. So I am constantly switching my charges and numbers, but try to make a very concerted effort when you're doing oxidation numbers to do the charge first, number after. And when you're writing charges, do the number first and the charge after, okay? So let's talk about how we find these oxidation states. And this slide seems really scary, but it's not scary at all once we kind of go through it. But atoms that are free, which means they're not combined with another element. So, you look on the periodic table and you see like magnesium. Magnesium and only magnesium when it's by itself is a neutral element. Its oxidation state is going to be 0. If you have O2, yes, oxygen is bonded to oxygen, but it's not bonded with another element. then it would be an oxidation state of 0. Simple ions, their oxidation state is going to be the same as their charge. So magnesium is in group 2, its charge is 2+, so the oxidation state is +2. Those that are in a compound, like here, sulfuric acid, H2SO4, all the oxidation states of hydrogen, sulfur, and oxygen in this case all have to add up to be 0. If it's a polyatomic ion like sulfate here, the oxidation state of sulfur and these 4 oxygens has to sum to the total charge, which would in this case be 2-. There are some unusual oxidation states, which we'll talk about in like a case-by-case basis, which is step number 6. And then we'll talk about some exceptions. So to start these 2 slides, circle them, highlight them. We'll work through a ton of examples. You see the next 2 slides are blank. So we're going to work a bunch of examples, and it's just going to come with lots and lots of practice, okay? So let's start. And I mean lots of practice to the point where you're going to be like, oh my God. And then I have more practice problems for you to get from the sub. So let's get started. Okay, so we're going to deduce the oxidation states of atom marked X. Pause the video if you need more time to write down these example problems, and then whenever you're ready, press play. All right, so if we go back to our rules, we'll see that this is a compound. So that means that we're looking at rule number 3. So this whole compound, the overall charge is 0. If it wasn't 0, there would be a charge on the outside, kind of like in B here. So everything has to equal 0. So we'll just go ahead and set everything equal to 0. We have 7 oxygens here. So 7 times the oxidation number of oxygen, which oxygen is a simple element. So that would be rule number 5. If you guys want to get out your periodic tables, find oxygen on your periodic table, and the oxidation state of oxygen is going to be equal to the charge that oxygen has. So since oxygen is in group 16, that means that its charge is 2-, so its oxidation state is going to be -2. There are 2 potassiums. And just like with oxygen over here, the charge and oxidation state of potassium are going to be the same. So find potassium on your periodic table. It's in group 1. So it has a charge of 1+, which means its oxidation state is also +1. And then we have 2 chromiums, which we don't know the oxidation state for. That's what we're trying to find. That's X. So now we just combine everything, move it to the other side, and solve for x. So this is negative 14 plus 2, that's negative 12. Move it to the other side, that's going to be 12 divided by 2. So that means chromium must be plus 6 as an oxidation state. So for the next one, we see that we have a charged ion. So we're going to follow rule number 4 here. So that means that just like before, the sum of all of these oxidation states has to add up to the charge. So that's a charge of -1. We have 4 oxygens, which we saw in the previous example that the oxidation state and charge are the same. So for oxygen, that's -2. And then we have 1 Mn with a charge of X. That's what we're trying to find. So just move everything to the other side and solve for X. And X ends up being positive 7. No, positive. Hold on, I can't math. -1 plus 6, 5. So that's plus 5. My bad. Right? Did I do that math right? Somebody double check me. Yes, positive 5. Okay. So then for the next one, this is another neutral compound, so that's going to be 0. We have 2 nitrogens with a charge of X plus 3 magnesiums, which is in group 2. So that charge is 2 plus, which means the oxidation state is plus 2. So then this time our X must be positive 2. Positive 3. -3. Sorry, -3. Okay. All right, now for sulfur, this is just sulfur. It's not combined with any other element. So that's going to be rule number 1. So the charge of this sulfur is just going to be 0. Now, this whole thing seems extremely scary, but I need you to take a break, take a breather. We're going to get through this. It's not a problem. All right. So we're trying to figure out X here. Now, this is a polyatomic ion, this whole thing, which is ammonium. Ammonium's charge is +1, and there's 2 of them right there. Plus iron, we don't know. Plus water. Water is a neutral compound, so its charge is 0, and there's 6 of them, but that's just going to cancel out to give you 0. Plus, we have SO2, which is another polyatomic ion. There's only 1 of them. Its charge is -2. And set that all equal to 0. So then you solve for X. So this just cancels. So we have +2 plus X and a -2. So that means our X must be +2. And in order to give us the oh, I'm so sorry, that two out there. So that's how you get +2. All right, so let's do lots more practice problems so that you can see a lot more of these. Because I'm really sorry, but I probably botched a lot of this and you're like, what the heck? So we're going to do the same thing. Okay, here we go. So pause the video if you need to, and then you are also going to need your periodic table, so keep those things out. And then we'll go ahead and start solving for X. So this is an overall neutral compound, so all the oxidation states have to add up to 0. We have 1 carbon, X, plus 2 oxygens, and the charge and oxidation state of oxygen are going to be the same, so that's -2. So then solve for X. X is going to need to be +4. B, we also have a neutral compound, so set that equal to 0. Hydrogen is, and we only have 1 of them, hydrogen's oxidation state is going to be 1. We look at the periodic table. Plus 1 chlorine, we don't know. Plus 4 oxygens, which is -2. Solve for X, and X ends up being +7. Now, if you feel like you're getting the hang of this, pause the video and work the rest of them, and then come back and check your answers. If you need to, you can keep following along with me. All right, so C is another neutral compound, so 0. There's 3 sodiums. Sodium on the periodic table is charged as +1+, so its oxidation state is +1. We have phosphorus, which we don't know. 4 oxygens, each with a -2 oxidation state. Solve for X. X ends up being +5. Now D, you see it's only oxygen, not combined with anything else. So therefore it's a free, uncombined element, and that oxidation state is always going to be 0. E is another neutral compound, so set it equal to 0. Phosphorus, we don't know. 3 hydrogens. Now hydrogen this time is still going to be +1. So then your phosphorus is going to have to be -3. Another neutral compound in F, set it equal to 0. X, we don't know. Chlorine is -1, so therefore X is going to need to be +1. G, another neutral compound, 2 irons, 3 sulfate ions, which the oxidation number and the charge for polyatomic ions are the same, -2. So that means that this has got to be +3. H, we have a overall charge, so set it equal to 3. Oh, I forgot to tell you, X, that's not bad. All right, cobalt, we don't know, so that's X, plus 6 ammonium ions. And ammonium, when it's not a polyatomic ion like NH4 plus, this is just going to be neutral. So that's 0. So then X has got to be +3. For this one, we have an overall charge of -2. Set that equal to copper, we don't know. Plus 4 chlorines, each have a -1 charge. So then X has got to be +2. All right, how are you feeling? Feeling better about this? You need a couple more? All right, well, now would be a good time for you to go ask your sub for the oxidation states worksheets. And you can work on those practice problems. Okay. All right, guys, I guess you'll listen to me tomorrow.